I'm sorry. Hello, everyone. Welcome to PyTorch NYC Meetup. This is our first meetup for the year, and we are very excited to collaborate with Meta and the Linux Foundation to host this event. So who are we? PyTorch NYC is a community and was started by a few folks in 2019, and they were taking fast AI online course. And the members of a community are data scientists, machine learning engineers, and people interested in learning machine learning. We're delighted to relaunch this meetup again this year. And I would like to thank Meta and the Linux Foundation for the support. I would like to thank Julia and Helen from Meta and Jen and Kali from the Linux Foundation for helping us organize this. I would also like to thank Reshma, who is the organizer, for her support. I am Deborah. I will be hosting the event. I'm a student at NYU studying computer science, and I have worked as a software developer before. Our speaker is Shashank Prasanna. He is AI ML open source and PyTorch developer advocate at Meta. He previously worked at AWS, MathWorks, and NVIDIA. He enjoys putting content creation and storytelling. Today, he would be sharing what's new in PyTorch 2.0. Thank you, Shashank, for accepting our invitation to be the speaker. Okay, we have a video, but I'm not sure if the audio is working, so I'll skip that. We have this question policy of, you can chat you can type your questions in the Q&A section, and we will be answering all the questions towards the end. This meetup is being recorded, so the video would be made available later. This is our first event, and we are experimenting with the format. So towards the end, I will also share a feedback form where you can give us your feedback so that we can organize future events and see what the community wants. Okay, so it's over to you, Shashank.
Awesome. Thanks, Deborah. Can everyone hear me okay? Thumbs up from folks who can hear me. Okay, I'm gonna share my screen. Someone needs to tell me that you can see my screen. There it is. Okay, is my screen visible?
Yeah. Yep, we can see it.
Okay, awesome. I'll just move the more faces away. And audio's okay, video's okay. Okay. Hi, I'm Shashank. I'm a developer advocate at Meta on the PyTorch team. And today I'll be talking about PyTorch 2. Now, I imagine some of you are existing users of PyTorch. Some of you may be new to PyTorch. Some of you may not have heard of PyTorch, in which case what's new is less interesting than what is it. In any case, I'll try to start gently, introduce some of the key concepts, and then jump into some of the new features that will become available in PyTorch 2. If you're following along the PyTorch development, PyTorch is in version 1.13 right now, and PyTorch 2 was announced last year at PyTorch conference, and version 2 will become generally available later this month. So this talk is about, it's been on release candidate and beta, so you can start using it today if you want to. So I've been using it last couple of months, and I'll be sharing some of the new features and functionalities in PyTorch 2. With that, let's get started. So before we jump into the specific APIs and the specific functionality in PyTorch 2, I wanted to take a step back and talk about, so PyTorch is a deep learning framework, right? It's a machine learning framework for developing neural networks. So take a step back and say, what is a framework? I want to set this up because this is important for some of the features that I'm going to discuss. So a framework is Python a framework? Is PyTorch a framework? Is Pandas a framework? Right? What is a framework? Right? PyTorch is a framework, and it provides the abstractions for developing neural networks, right? And some of these abstractions, and I'm just going to show here, it could be the torch.nn and FSDP for distributed training. There's the torch.tensor, and there are a bunch of APIs and functions that you can use to interact with the framework so that you have a certain goal in machine learning, right? This specific framework is domain specific, right? PyTorch. It's not a framework for everything. It's a framework for a specific subset of machine learning, right? So that's a framework, and the top where I drew the arrows, this is how the user interacts with the framework. So this is all UX, right? This is the developer interacting with the framework, calling APIs, and you expect things to work as they should, right? If you create a tensor, it should create a tensor. If it runs, if you wanted to distribute a training on large language models, then it should do that for you, right? You interact with the layer. But on the flip side, on the other side are hardware on which the framework runs code on, right? These could be your CPUs, your GPUs, and other specialized machine learning hardware. Like there are Google TPUs, AWS Training Inferentia, there's Intel Habana Gaudi. There are a bunch of other hardware accelerators as well. Obviously, Google, NVIDIA GPUs are the most popular ones that you may be using. Now, you don't really think about that other than the fact that is there a hardware available for me to run code, right? Outside of that, you don't really think about, you don't have to think about the how it runs code, right? As far as the UX is concerned, PyTorch is really known for its eager mode operation. And if you're a user of PyTorch, you know that it behaves like Python does. You can debug it. Every line of code executes as you go along. You can look at outputs, which is different from some of the other frameworks where you need to build your graph and then go run it like a compile language, right? This is an interpretive sort of way of running it, okay? And then it's Pythonic, as Soumit likes to say, it's Pythonic. It's largely written in Python. It behaves like Python. It has a friendly interface of Python, and it has very, very good abstraction for the things that you want to do. So a framework really provides these abstractions to define tensors, to develop your training loops and run, okay? And oftentimes you don't think about what's under the hood and you expect good performance. But a lot of the capabilities that we will discuss are actually going to be the under the hood capabilities here, right? These are all the performance optimizations in PyTorch 2 that will give you the performance that you expect. Now, let's talk about, before we jump into some of the specific, features, I'll take you through an example, and let me go look for my browser here. Okay, so I have a couple of examples. So through this talk, I'll be interspersing some concepts along with code examples, so you get an appreciation of the APIs, but also of the technology under the hood that makes this interesting. Okay, so if you're wondering where I'm running, this is a Jupyter notebook that's on AWS, and I have a GPU which you can look up using NVIDIA SMI. So there's a GPU and NVIDIA A10G GPU. So it's the latest generation GPU. It's fairly powerful. It's not the most powerful, but I'll be using this for my examples. And a lot of the performance benchmarks I'm going to show you are obviously going to be subjective to what kind of model you have and what kind of GPU you're going to be running on. So if you're familiar with PyTorch, some of these packages that we load may seem familiar to you, right? So I'm going to start executing this notebook. So you load Torch, Torch Vision models, right? I'm going to set some flags here that optimizes for the latest generation of GPUs, specifically this Matmul Precision High. Make sure that it uses the latest tensor cores on the GPUs, the TF32 precision primarily. And then if there's a GPU device going to run on GPU. So, and I have this helper function which can run benchmarks. So I'm going to run that. And what I want to do is run 3 different networks and show performance improvements. And then we'll talk about how we are getting these performance improvements in PyTorch too. So first we will run a ResNet 50. And if you're familiar with computer vision, ResNet 50 is a computer vision model. It's quite old. It came out several years ago by now. So what I'm running here are 2 steps. First, I'm going to run this model just as it is. Okay, this is the model I just get this model from the model from Torch Vision models, and I just run it. And next, I'm going to run this special line of code here, which is new to PyTorch 2. It's called torch.compile. Okay, it's just one line of code. Essentially, it takes in your model and it creates an optimized model. So torch.compile of your model and creates an optimized model. Okay, one line of code, no other changes. And then I again run a benchmark. And this benchmark is just going to, if you look at this helper function, it's just doing some warm up and running it for several iterations in order to get sort of the median and a percentile. Now, if you see here, I get about 7% speed up. Okay, one line of code, right? 7% is not huge, but for a single line of code change, that's pretty good, I think. And of course, your mileage may vary depending on what model and what GPU you're on this on. Next, what if you had a custom model, not the ResNet model, but you have to implement your own? I've just, for illustration purposes, just created a couple of layers here. And I'm again going to do the same exercise. And with a single line of code here, I compile the model and I get about 18% speed up. Okay, you can run this several times. You'll find some fluctuations there, but more or less, you will see between 18 and 20% speed up for this specific model. And notice here I specify something called a backend. A backend is the compiler technology that's under the hood, and there are a few different backends you can choose. So that's where the magic is happening, and we'll get to that. I just want to show how easy it is from the top of the layer, the user experience point of view. Then I'll talk about the bottom part, which is how do you optimize, how does it optimize. Last, I have a Hugging Face example here, and I'm just going to run through it. And again, we'll talk about speed up. The same one line of code here called torch.compile, you see, and I've added an extra parameter here called max auto tune. And I'll again talk about what these things are, but there are different modes. Some of them, max auto tune takes more time to compile the model, but may give you better performance. Now, whenever you compile something, right, there's an upfront time cost. You're going to be spending some amount of time compiling the model so that you can reap the benefits of the compiled performance later on, right? So that's what I do. And with max auto tune, it takes more time to compile to generate better high performant code, and then I get about 6% speed up. Okay. The purpose of this demo is not to show you how it optimizes and what the performance numbers are. In fact, on our PyTorch 2 blog, we speak about the specific performance benefits across the board, across popular models in Hugging Face, Torchbench, and TIM. And I'll let you read the blog post for those specifics. There's a leaderboard, there's a dashboard where we're tracking all the performance improvements. It's all open source on PyTorch. But my goal was to show you it's a single line of code change to get these performance. Okay. Now let's go back to our discussion here, and I want to talk about now how are you getting performance, right? So we spoke about we get performance by a single line of code. How is PyTorch getting you these performance benefits in version 2? Well, there are a couple of things that happen behind the scene when you compile. First, you have to get the graph. A graph is a computational representation of your graph of your model. We'll come to that. But once you have a graph which represents your layers and operations, there are a few things you can do under the hood to speed up. One is graph optimizations. When you can look at your entire model, unlike running it in eager mode where you're running through each step by step, when you have the opportunity to look at your entire graph, you can find opportunities to do vertical fusions. You can fuse different ops together so that there's less overhead when you run this on hardware. And I'll show you an example of that. Also, when you look at the entire graph, you have the ability to run operations out of order if there is no temporal dependence there, right? If there's some operation in the future that can be executed, you can do that. There's also automatic work placement across multiple devices. These are all things you can, performance gaps that you can exploit when you can look at the entire graph where during the compilation phase versus running something in an interpretive way, in a step-by-step way. Okay, so to give you an example of what I mean by graph fusion. Now, if you take a look at a graph, now I have here, what do I have? I have convolution, bias, ReLU. These are your normal, layers. Convolution, bias, ReLU with a different filter size, max pool. Now, when you look at this, every time this box is executed, it's executed on the hardware as a separate kernel call. Let's say if it's a GPU, there's a convolution kernel that's invoked, and then the data is executed, and and it comes back to your Python code. Then you invoke the next operation, bias, and then the next. So each time you're launching different kernels, that's potentially an opportunity for reducing torque overhead between your process and GPU. Instead, what if you could combine these into a single function, right? For single kernel. And similarly, what if you could combine this into another one and maybe a third one? And then what you end up is, rather than having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ops here, you can have 4, right? So now you have lesser kernel launches on the device, or fused operations. So these are called vertical fusions. Also, because you know what kind of data is coming in, you can also combine them when you write them into memory. So rather than allocating different memory, allocating different locations, you can write them in a strided fashion. So because rather than running another concat operation, you can just write them together in hardware. Again, as a user, you don't have to worry about this. This is stuff that happens under the hood by the compiler. This is why you would want to compile. Now, there are a few different things that happen under the hood when you say torch.compile. Okay, again, to re-emphasize, it's one line of code for a user, which is you and me. We don't need to worry about what's happening under the hood, but I'm sharing this because there's some you can appreciate what's happening under the hood. And secondly, if you're trying to get this extra performance and you run into some hiccups, right? I'll show you how to debug and how to take a look at what's happening under the hood, so you can actually appreciate what's going on. So it's not a closed box thing. You can see what's going on. A large part of it is Python, very readable until you get to the hardware backend level, in which case it'll be device specific code. Even there, if it's GPUs, it generates Python code using Triton, which I'll show you in a moment. Now, there are a few things that needs to happen. First, when you write a code, you need to acquire the graph. The graph is your computational graph, wherein you define your layers, your convolution, bias, ReLU, any other, even control flow, anything you have, right? That's your graph, your computational graph. You're adding stuff, you're multiplying stuff, whatever you're doing, right? ReLUs, GeLUs, whatever you have. That's all part of your graph, and you want to acquire it and store it. So there's graph acquisition. Once you have the graph, remember, with deep learning, you do the forward pass, but you need gradients in order to train the model. Gradients come from your losses, right? If you recall, gradients are used to head the weights in a direction which minimizes the loss, right? The gradient descent, stochastic gradient. You need gradients. Now, you want to propagate the gradients back, so you want to capture the graph will look different when you find a derivative, right? When you go back, let's say if your model is just x squared, right? Derivative of that is 2x, right? You propagate back. So potentially, like you have this forward graph, which is also the same graph you use for inference when you deploy your model. Then your backward graph, which propagates the gradients and adjusts the weights. So it's weights time learning rate times gradient, right? You head towards the minima. And then you have these two graphs now. And then what the compiler does is lowers it. Lowering is the concept of, in PyTorch, you have over 2,000 different ops, right? Now, if you want to run this on hardware like a GPU, or even let's say you're building a new hardware, you can't support everything under the sun on the hardware. You have fixed real estate and fixed silicon space. So you support a subset of the ops on the hardware, and some of those ops are specialized for hardware. And then the lowering is the part where you take this big subset of ops and reduce it to a small subset that can then be run. And finally, the backend compiler is a compiler that's very close to the silicon. So if it's GPUs or if it's some other backend device, then it's the compiler that would target specific silicon features. Google, NVIDIA GPUs, latest GPUs have tensor cores and specific precision type. So their compiler or targeting those specific features in the hardware would give you better performance, right? Like if you want to, tensor cores have the FMA, they call it, right? So it's like fuse, multiply, add in reduced precision and accumulate in single precision. So it's a very specific hardware feature, and you want to exploit it so you get better performance. So those are things that happen under. And broadly, all these capabilities are covered under the hood. So all of this I'm showing you is torch.compile, right? All of this, right? It's all of these things are under the hood, torch.compile. So there's TorchDynamo. I'll talk about what these are. AOT ahead of time AUTOgrad for getting those gradient backward prop. 810 prims, I'll talk about what those are. Those are the lowering, those subset of the overall ops that are supported, and finally TorchInductor, which is the compiler. Now let me go back to the code example to show you what that looks like. So we saw the benchmarks, that's great, single line of code, right? Now I want to show you an example where we can take a look at the graph. Now I have a very simple, it's not even a model, right? It's two ops, sin x, cos y, and add them up. Okay, very simple, right? So I'm going to run this, and I'm going to run it through the compiler. Okay, there's a reason I'm doing this. I'll tell you why. So I'm going to run it through the compiler, and once it runs through the compiler, I set on the debug mode. So unlike the previous steps, I have debug mode on, and the debug mode will give me some additional information about what the graph looks like. I'm also going to capture the graph without the optimization. So I'm going to open both those and compare. So this is the graph that is the original graph, which is, you see here, there is a sin x, and there's a cos, cosine, right? Your x value comes in, your y value comes in, you apply these operations, and then you add, okay? Operator.add. And then there's your output, okay? This is exactly this code, right? X comes in, Y comes in, sine, cosine of it, and you add them up. Now let's take a look at the optimized graph here. So I'm going through a couple of folders, but I will tell you forward, backward. I'm going to go to forward, and I should have a graph here. Aha, what do I see here? So I have another graph here that looks slightly different. So rather than have a separate sine op and a cosine op and an add op, what I have here is a combined op. Let me zoom out so you can see this better. So I have a combined op. So this thing implements all of these things. Okay. So that's what the compiler does. Now, when you have fewer functions, you have fewer kernel launches on the hardware and more opportunities for optimizations, right? So this is graph fusion. Okay. So this is what we call graph fusion in the thing I demonstrated earlier, right? So I will also show you. So this is the two graphs that I showed you before and after. I will also show you what the graph capture looks like. Now, if you look at this debug folder, so when I switched on debugging, and you don't need to do this, you need to do this if you want to learn more about what's happening or if you want to actually debug. There's a directory here called AOT TorchInductor. So if you recall from our presentation here, so you see this AITAutograd, right? And TorchInductor. So basically, and this happens in between. So basically, it's showing some debug information about these steps that's going on under the hood. Okay. And if you go back, look at the forward, I look at the FX graph. So this is lower level IR or intermediate representation of the model that you had in PyTorch. So you had your sine, a cosine, and then here you see here they're being re-implemented by a lower level sine. You see this sine here? Uh, this is sine and this is cosine. It's being re-implemented by lower level ops here. This is the same model as the one you had, but it's being re-implemented. And this is this TorchDynamo capturing the graph. And then after it goes to the last stage, which is the TorchInductor phase here, the TorchInductor phase, that's what targets a specific hardware. Now, if you go back and look at the output code, you'll see that what the compiler does is it'll generate lower level GPU code that can be compiled into GPU kernels. So there is this code that was generated in output code, which is under these quotations as a string, because it's then going to use that code to generate a GPU kernel code. Now, GPU kernel code usually written in CUDA, right? Most of you and I don't write CUDA. I imagine some of you may write CUDA, but most higher level PyTorch users don't write CUDA code. But this automatically generates code that can then be converted into CUDA. And this is, if you take a closer look at this, you'll also see here that it generated a single CUDA kernel for sine, cosine, and addition, if you look closely, right? So it took your PyTorch code, generated a lower level IR, and eventually fused them and created a single kernel call for sine, cosine, and the addition, the 3 steps. Okay. Now I'll show you something interesting now. So this ran on a GPU, right? And I know that because I set to CUDA 0, right? What if I remove this? So now I will not run it on a GPU. I will run it on the CPU, right? So I'm going to run this again. And what it's going to do, because I have debugging mode on here, it's going to generate another graph for me, which I should find forward here. Now let's take a look. The graph won't look different. The graph will look similar, but the code is now going to run on CPU instead of GPU. So if you take a look at the new code, it looks very different. So this is CPU code. This is not GPU code anymore. This is not code written by Triton that would generate CUDA kernels, but this is actually code that will run on CPU. Everything happens under the hood seamlessly. You don't have to worry about it. But that's the beauty of Torch compile, where all the optimizations happen seamlessly under the hood. Okay. Now, okay. So I showed you the before and after graph fusion, which is exactly this, what I showed you, right? So it's exactly this I showed you the fusion here, the fusion here, fusion here, and that's exactly the same fusions I showed with that's to sine, cosine, and addition. Good. And the graph that was generated with the lower level IR, that the A10, the Dynamo captures the graph. So there's no 1:1 mapping here. They all share some responsibilities here. So Dynamo does graph capture, and AITAutograd is responsible along with Dynamo to generate the forward and backward graphs, and it also does the lowering. And I'll show you a last demo, which is a little more advanced, wherein you can actually go and customize some of the things that's happening under the hood, which most of us won't need to do unless you're writing a backend compiler, right? And lastly, the TorchInductor is the one that generated the CUDA kernels or the CPU ones, which are depending on which you are targeting, whether you kept the device. Now, how does the stack look like, right? Basically what I said, you have your PyTorch model, and TorchDynamo captures your graph, right, into FX graph, and this is written in Torch IR. Torch IR is not the lower level IR yet. It's an IR, but it's not down to the really low level IR, and I'll show you the breakdown here. And finally, the really low level IR is then consumed by the backends here. So there are some backend examples. So TorchInductor is the backend that we used. I showed you. So TorchInductor will take those really low level IR, and then because it has knowledge of the device, whether it's a GPU or whatever it is, it can now say, oh, I have all these low level ones. If I combine this in certain ways, then I get better performance out of my hardware, right? So it's going to do all of that. You don't have to worry. It's going to do all of that. And there are other backends, and these are, other hardware providers can make their own backends as well. All right. So this is the slide I wanted to talk about, show you the large set of ops in PyTorch that you write in, you and I spend our time in, and then how to reduce all them to a small subset, right? So way back here on the left are the entire PyTorch, about 2000 plus different ops, and this includes everything, your torch.tensor, torch.nn module stuff, like everything there. They all are here, your addition, your multi-matmul, everything, right? And then they can be further compartmentalized into different categories. And then the lower level ones, which I showed here, these A10 prims. So these are the lower level ones here. And the reason we want to do that is compilers like your GPU ones or other hardware, it's easier for them, people who write compiler backends for those hardware, is easier for them to work with those. Also, there's lesser complexity in your code, right? So the interesting thing about TorchInductor is it's Python all the way down. Even in this example I showed you under the debug. So even if you go look at the lowest of the lowest level, it's still Python, right? This is where's the output code? Yeah, it is still Python, right? Even the CUDA code that was to be generated from uses a framework called Triton from OpenAI, and the Triton code, this is called Triton. So the Triton code is also Python code. This is Python code, which means you can debug it, right? It's easier to debug. Now this Python code is then used to generate the low level CUDA code, and you don't have you don't see that as part of this compile stack, because the TorchInductor will do that for you, right? So that is to say that the stack from where the user interfaces all the way to as low as generating optimized code is all in Python, which means people who really care about performance, it's more hackable, it's more easier to read and consume Python code than, lower level hardware code or C, C++ or anything else like that, right? Okay. And let's see. Okay, not yet. Thank you. I have another demo. All right. So I show. Let's take a look at another demo. This one is going to go a little deeper, just to show you the stages. So you see these stages here. These stages as it goes down. I just to show you those stages, how the code, permeates through the compiler, for lack of a better phrase. Again, I want to pull our conversation back to what I said in the beginning. It's just a single line of code for most of you. Where is that? Here. Okay, torch.compile. Okay, that's all you need to do. What I'm showing now is what's happening under the hood for those who are interested in seeing. And so let's see. I import TorchDynamo, and I define a model, and it's very simple. Again, it's just linear layer and a GELU activation. Okay, there's a reason I chose GELU, and I'll show you. So it just shows the lowering better. Okay, so you initialize the model, you select your device, And then what we do here is something interesting. So again, the same torch.compile, but rather than provide torch inductor as a backend, again, if you recall, there are a few different backends, right? There's torch, there's torch inductor, there is NVFuser, there is AI template, a few different backends. But what if you were to write your own backend, right? You would fall into the third category here. If you were to write your own backend. Now, well, that's what we're trying to do here. So let's say we don't want to write a backend, but we are using this as to intercept the information that's passed to the backend. Okay, so we define a toy backend, and we provide that toy backend to compiler. So it's not sending it to inductor in order to get the compiled model, but we're going to intercept the information that comes there and print it out. So if I go ahead and run this, I will see that the Dynamo doing its job, TorchDynamo. So Dynamo captures the graph and it prints out this similar to what we saw previously. Now this code is, you'll see here in the comments here, the code that corresponds to your model, and below that you see the lower level code that after graph capture, right? So the IR from that. So it's showing the comparison between the code that's in your so it is not that different, right? So there are a few different implementations here, but it's not that different. We haven't lowered it further. Okay, so all we're doing is when you call the toy backend, it gets the graph and we just print it out. Okay, we just print out the graph. Okay, graph module. Next, we'll take it one step further, and what we'll do now is, let me go ahead and run this. Okay, so now we are going to run so this is just the forward pass. So when we ran this, we only got the forward pass. There's no backward pass here. Okay, we just intercepted the toy backend, we just printed it out. And now when we use AOT ahead of time, AutoGrad, right? So we get the backward pass too, right? So we have this no, this does lowering actually. First, we did not run backward, I think. Did we run backward? Oh, we didn't do backward. So this just does a lowering. Now take a look at the ops that are used here. So now the ops have changed to A10 here. You see this A10, and same with Gelu. I'll let you compare here. So this is torch ops A10 Gelu, and if you scroll up, it said torch CNN Gelu. Okay, so it's done graph lowering into the A10 ops, which is a smaller subset if you recall. It's like the 250-ish ops compared, or I need to check the numbers. The prim I need to check, but it's a lower subset of the 2000, right? And then you see that. And finally, you can, once you get into sort of the target hardware, you can further decompose simple things like if you had Gelu here. Gelu is actually is the conditional distribution of the normal Gaussian, right? So you can actually decompose into the components, right? So the components of Gelu. So you can, if I run this, what we take a look at now, this whole implementation is Gelu in lower level. These are your lower level ops, right? You see the error function here, the multiplication. So yeah, so you can keep going lower and lower. And again, the whole point of this exercise is just to see what's happening behind the hood. Doesn't really affect end user unless you want to go and take a look at it further. And you can then further lower it into the PrimTorch. I think the PrimTorch is the much smaller subset, and it's in the document. So the PrimTorch takes the 2000 ops in PyTorch are mapped into 250. Okay, I think 810 I believe is still higher, 700 or so, and then PrimTorch is the really low level. The key difference is that you don't want to go that low unless you know that your hardware well and you can do all the fusions yourself. So your compiler is responsible for gaining the performance back. That's why for most people, you'll just use whatever's out of the box. Okay. So anyway, so that's the last example. And finally, I have an example that I won't run, but I'll just show you. What if you had your own custom model and you wanted to use torch.compile, right? So here's an illustrative example. I don't see much performance improvements here in this example, one, because my model is so small. Secondly, I'm not using the best GPU that is available today. So I would highly encourage you to take a look at some of the benchmarks that are available on PyTorch GitHub. There's some tables there showing the performance improvements across popular models in Tim, Torchbench, and Hugging Face on what kind of hardware. So I will just show you what it would look like. So you define your model, your transformations, your data loaders, and all that, right? So literally, there's one step here where oh yeah, so first I run this without any compilation, and if I want to compile, I just add this line of code. So I would say I would get the model. I would get the model here. And once I get the model, I would call torch.compile, inductor as a backend, and I say max auto tune, if you recall, is it spends more time compiling, but then it'll give you, it'll try to give you a more performant model, right? So no guarantees there. It depends on your model. Try to give you a more performant model. Yeah, and then yeah, then you can go try. I think I trained this for yeah. So yeah, I didn't see performance improvements on this model. I think it was the same 16 minutes. But on larger models, like on some toy example models, I showed you the performance improvements, and I highly recommend you take a look at the examples that's on the blog post and others for performance improvement. Okay, so just to go back and sort of recap, right? The only thing that you need to remember is there is a whole list of compiler technologies under the hood, and Torch compile is a single line of code that lets you leverage all of that. And if you do want to take that route, if you feel that you're getting stuck, or it's not compiling, or there's it's compiling but there's no speed up, or if it's not compiling, then which stage is it blocking, right? Is it failing in the graph acquisition phase? Is it failing in the lowering phase? Is it failing in the torch inductor phase? So if you go that route and you have a custom model, exotic model that's not compiling, then it's good to know these tools that I shared with you to go debug and go figure out where the issue is. The best place to learn about what is new is a PyTorch 2 blog, but I also the latest doc in the first you need to go to PyTorch doc and check the master for the latest documentations on torch.compile. And here under getting started, excuse me, there's a lot of information on the different backends that are available. Like Inductor is a backend. There's also NVFuser and a couple of other backends. And there's also a troubleshooting guide. If you ever, the thing that I showed you was the debug mode, trace enabled. So that'll let you debug. And let's see, custom backends, troubleshooting. Yeah, so this is the best place to learn more about all the new compiler options and all that. Our last thing is torch.compile is under torch. So let's here compile. So here are a couple of options I showed you. You send the model. You can optionally say full graph. Full graph means that your entire graph is supported and there won't be any graph breaks. So one of the reasons you won't get performance improvements if there are graph breaks, and there are helper functions that will tell you if there are graph breaks, right? Because of some reason, some unsupported thing, there's a graph break. So it'll give you better performance if you do this, if you know that your whole model is supported, right? Like something like ResNet 50, so you can, if you want to. Dynamic shapes, backends, I spoke about Inductor, but you can run Dynamo, torch.dynamo list backends, and I'll show you a list of all the backends that are available. Yeah, let's see if I run it here. Yeah, so these are all the backends that are available. Inductor, the one we used. What else? Mode. I think we discussed max auto tune, and there's also reduce overhead for reduction in overhead. Again, these are all options. The options dictionary is where I pass those debugging things. There's other ways to do it. You can also set an environment variable. I think it's called torch debug, compile debug equal to 1, I think. So again, it's in the docs here. I would encourage you to take a look at it. So I think before we close, I also want to share that all I spoke about was torch.compile, because that's the big part of it, performance improvements, while keeping all the benefits of PyTorch, eagerness, eager mode, execution and all that. So I think this is a huge step for PyTorch. I'm really excited about these. But at the same time, there are a host of other new features that are coming out. Domain-specific libraries as Torch RL, Torch. Those would be separate conversations and discussions. But I will encourage you to go to the PyTorch YouTube channel. So what we've been doing the past couple of months is a bunch of us, we've been interviewing engineers on the PyTorch team about new features. Now, if you go to the live section in the PyTorch YouTube channel, we've been interviewing, again, I am not the engineer who built this. I'm just a user like you. We have interviewed the folks who build these features for deeper dives. So if you take a look at this, there's a deeper dive on TorchDynamo that we discussed. FSDP, this is your distributed training, right? Export, how will export? This is an important question, that how will export work with torch.compile, FSDP, inductor backend, and data loader, Hugging Face support, Torch, reinforcement learning, how does dynamic shift. So these are all deeper dive conversations. I encourage you to go check it out if you want to learn more about 2.0 features. And call to action, I would say, if you haven't tried, go check it out. It's in the nightlies and release candidate. I'll pause here and we can use the next 10 minutes or so to answer questions.
Thank you so much, Shashank. I'm going to read a couple of the questions and then I'll let Deborah read the other ones. The first question, which I'll just take from the Meetup discussion, is IR short for intermediate representation?
Yes, I'm sorry for glossing over that. Yeah, there are several stages of intermediate representation that come through every step, right? So from the graph acquisition, you get the IR here, and then you get lower level with lower. It keeps, yeah. There's several IR phases through the. The interesting thing is, like, you can intercept at any point you want. If you were on the hardware side of things and you can intercept at the A10 level or the higher level. So yes, IR is intermediate representation.
Okay, the next question is from Vishal. Is this similar to what is done with an Onyx model? Some of these might be difficult because the questions don't line up. We didn't ask them exactly.
That's okay. Yeah, we'll try and answer them, like, I guess, speed run. This is for training, right? So Onyx is your export path to deployment, whereas torch.compile accelerates your training. Like some of the examples I showed you, because you're generating these optimized graphs forward and backward, and TorchInductor is generating these optimized kernels. If you're targeting GPUs or other devices, CPUs, those are the two supported on a TorchInductor, you're just getting faster training performance, and even 5%, 10%, 20%, that adds up if you're training for like days on end, right? So it's mostly the first time we have like a training focused. There have been some efforts in the past, but this is all coming together with torch.compile.
Okay, and the next one is Vishal also says, very impressive. Thank you for the low-level explanations. And I'll let Deborah do the rest of the questions.
Okay, so we have one question asking if these notebooks can be shared.
Yeah, I couldn't figure out hosting it just before today's talk. So yeah, this is all stuff. But I will say, like, most of this stuff is already either in the documentation or in some of the blog posts that's there, but it's not all in one place, and I'm happy to share it. I'll figure out a way to put it publicly, like GitHub or something, and share it with the organizers so they can put on the comments, or I guess, right, on the recording of the video, so people can access it. If I'm not, if you want to follow me on social media or something, I'm happy to like share it when it becomes available also. But if you don't want to, that's fine. I will share it with the organizers and they can post it in the comments.
Okay. Another question, are we losing some functionality by doing the compile? If yes, what are we losing?
I At a high level, no. I mean, if it doesn't compile, then it'll complain to you that it's not compiling. I guess there are some further nuances that I'm not an expert at, which is like, um, for example, I think in our interview with the distributed training team, it's on the way, right? But it's not available today. So if today you may not have some features, right? And again, it's not GA yet. So if you try it and if something's not working, one, we would like to hear about. Second, like, we would like contributions as well. So if you are interested in contributing, that's great. But without going to any specifics, I don't, if it compiles, then it should work. The issue you might have is listed on the PyTorch webpage, which is if you go to the frequently asked questions, there are a couple of questions like, if my code is crashing, what do I do? Or if there are errors, or in some cases its compilation is slow or the output is slow, right? So those may be things that you might be more concerned about initially, I guess. But yeah, I'm sorry, that's a very high level answer, but without I'm not even, I'm not the right person to know at the depth level if there is things that are not supported. But I encourage you to watch those videos, because we've interviewed the experts in some of those, especially the Dynamo and the Inductor one. You might uncover some stuff there that I didn't cover today. Here, go watch those.
Okay, one last question. How to compare PyTorch compile with TensorFlow's compile?
I don't have experience using TensorFlow, so I can't comment. Yeah, I guess that's my answer. I mean, this is the project that we are excited about, right? I mean, if you're a PyTorch user, then you will enjoy it, I suppose, right? And if it's giving you the performance, people already love PyTorch for what it is. It's easy to use. It's Pythonic. It's hackable. I'm using phrases that people tell us of what they like about PyTorch. And if performance was a thing on your mind, this is going to address that too, right? So basically, you hopefully get everything that you're looking for in a deep learning framework.
Okay, two more questions that we'll quickly go over. One is, what is the best path to begin contributing? And the second is, does the compile generate specific kernels for the Google TPU as well?
First question was best part to contributing. There is a contributing dot if you go to the PyTorch GitHub page, you should find contributing guide, contributing.md. So there's a separate contribute. So it's a pretty detailed guide that talks about how to contribute. Again, I think you don't have to, contributing doesn't have to be code. Contributing could be raising an issue, fixing a typo, telling us something is not working. I mean, they're all contributing to open source, right? Again, if you want to, fixing bugs would be the next level. And then, of course, building features and capabilities, that would be even more involvement. So there is contributing.md guide, and that's also there for the tutorials. There's a separate contributing guide for tutorials. So if you want to contribute that way, that's great too. And what was the other question?
Does the compile generate specific kernels for the Google TPU as well?
So the backends that I shared are the only ones that I mean, I guess I listed the backends. So those are the backends that are available. I mean, it's not. This could be a backend there, but not with the way we have today. These are the only backends that are supported right now. So,
All right.
and yeah, you can list all the backends. These are all the backends that are supported. So if you want to contribute a backend for TPUs, I think we would more than welcome it. All right.
Okay. So I have shared a link, a form for a feedback that you could fill. We are looking for feedback regarding like events and what are the preferences. So based on that, we will be organizing more events in the future. Yeah. Thank you, everyone, for participating, and hope to see you soon again. Thank you.
Yeah, thanks for your time. I know we're really appreciative of you spending 1 hour with us out of your schedule. So thanks for joining us, and thanks for listening to me. And if you have questions, feel free to reach out to me in any one of these ways. Thank you.